Um, the topic of rods and clocks in relativity theory used to be the central topic of the philosophy of space and time. From Schlick to Grunbaum, this was the central topic of the philosophy of space and time. Then this topic clearly lost momentum in the late 80s, probably, because of the emergence of a new topic, which was much more interesting, probably the whole argument. But in later years, this issue came to the fore again. This is mainly, I think, because of this book of Harvey Brown, Physical Relativity, which is a very influential and very provocative book, where Brown tried to support what he calls a neo-Lorentzian approach to relativity theory. To support this claim, of course, he uses systematic arguments, but also historical arguments. And he tries to, most of all, to use Einstein authority to support his claim. The argument runs roughly like that. Einstein, at a certain point of his career, so at the beginning of his career, was an operationalist. He treated rods and clocks as primitive, unstructured entities. Later on, at later his career, he recognized that actually rods and clocks were structural dynamical entities, composite bodies, very complicated, regulated by physical laws. According to Brown, we have to understand this opposition using Einstein's distinction between constructive and principal and constructive theory. Einstein introduced in 1919, or even earlier, actually. So the story goes like that. Special relativity, maybe even general relativity, was a principal theory. So rods and clocks are treated as black box. But actually, Einstein wanted to build a constructive theory, and so he wanted to give a dynamical explanation of rods and clocks. At the end, what we will have a theory in which space-time will have a parasitic existence, will be a consequence of the physical laws governing the material structures of rods and clocks. My goal here is to try to understand what in these reconstructions, right, taking occasion of this suggestion by Brown, to try to understand which was Einstein's position toward this issue along his career. So we are celebrating Einstein, and my humble aim of this talk is simply to try to understand, using historical sources that we have at our disposal, what he really thought. And I think this construction will turn out to be only partially correct. So I think Brown is correct when he claims, in the first two claims, it is absolutely true that Einstein uses rods and clocks and structural entities, but he recognized that actually they were very complicated composite systems, even if we will see he did that at a very earlier stage of his career, actually already at least in 1917, he says pretty clearly, and he never changed his mind all over his life. But I think the second part, so to say, is not supported, at least by textual evidence. So I don't think we should use the opposition between principal and constructive theory to understand Einstein's attitude toward rods and clocks. And most of all, Einstein was not interested in the question of the ontological existence of space and time, if it depends from rods and clocks or the other way around. Einstein was interested in a more well-known epistemological problem, or the relationships between a theory and experience. Before I start with a more historical reconstruction, I will simply sketch in an abstract way the main line, or I think the argument that will be the background of my reconstruction. So the story goes roughly like that. So special relativity and general relativity presuppose the existence of physical systems that can play the role of identical constructive rods and identically constructed clocks. This means that at relative rest, they measure the same unit of time, the same unit of length. So we can bring them carefully together at rest again, and they will always measure the real proper time, the real proper distance. However, special relativity and general relativity do not provide any clues for assuming that physical systems with these characteristics really exist in nature. So we have to start with the provisional identification. After the provisional identification has been made, then the theory is said to be empirically testable. For instance, we can say that atoms could play the role of identical clocks. We know that all atoms are perfectly identical. So this is a good physical system that can we use as an identically constructed clock. Then we observe two atoms moving in uniform motion in respect to one another, and special relativity predicts that we will observe the so-called transverse Doppler effect. We observe it, then the theory is correct. We observe in general relativity two clocks moving along different trajectories in space-time. So general relativity predicts that we will observe the redshift, the gravitational redshift. If we observe this phenomenon, then the theory is correct, put it, of course, very roughly. However, a problem emerges. So rods and clocks are actually very complicated systems governed by complicated physical laws. We don't have any way to say in advance if our systems would be a good clock or a bad clock, or a good rod or a bad rod, without knowing the laws governing the systems. So rods and clocks should not be treated as physical. Actually, in principle, rods and clocks should be treated as physical systems just like any other. So we will need a special relativistic or general relativistic theory of matter, which admits solutions, stable solutions, periodic solutions, with some characteristics that make them suitable to be used as rods and clocks. Of course, here then the theory will be able to control its own means of verification. So the question emerges, what does it mean to compare the theory with reality? So the whole question Einstein was discussing can be summarized. It is a quote by Einstein himself when he says later in life, of course, as a joke, is simply Pilate's famous question, what is truth? What is double quote from, of course, from the Gospel. So 2 points are worth to emphasize. First of all, we need a dynamic explanation of rod and clocks. Einstein will agree on that, but not as Brown claims to explain contractions and slowing down of clocks, but the opposite, you might say. So put it provocatively, one can say we need to explain the existence of rods that never contract and clocks that never slow down. When they brought back together, again, they will always measure the same proper time, the same proper distance. That's the first point of the distinction. Second, the problem is an epistemological problem and is not connected with the question of the ontological status of space-time. So it's a classical problem. How can I compare my theory with experience? The talk will follow closely the chronological development. I think it is important to show, in this case, how Einstein's opinion did not change along the years, was very constant. So we'll start with 1917 is the first quote that I can show where Einstein clearly addressed this question. Then we'll enter in the 20s. Einstein will force to go public, so to say, and to discuss that in a public debate. There are several other works in the later years where Einstein clearly developed a two-stage strategies regarding rods and clocks, a provisional and a principal one. And finally, I will go to the later reflections, especially the one in autobiographical notes, which are very famous. Before I start with the real question of rods and clocks, I would like to mention this passage, which apparently has nothing to do with what we are discussing, but I think it is important. As a passage, as many of you might know, is from lecture notes 1911, lecture notes on electromagnetism. Here Einstein is discussing the particular case of a continually distributed electricity, this is charge. I quote, "We have seen how experience led to introduce the introduction of the concept of charge. It is defined by means of the forces that small electrified bodies exert on each other. But now, in the case of a continuous distribution of charge inside of a pondable bodies, we extend the application of concept to cases in which this definition cannot be applied. So in this case, we don't have the charge attached to the small bodies. The charge is smoothly distributed, but still we can use the notion of charge even if in principle our definition is no longer applicable. Here too, we can define the vector electric field strength as the vector of the mechanical force exerted on a unit positive electric charge inside of a body, even if the force so defined is no longer directly accessible to experiment. Why we can do that? We come to the important part, because we establish a conceptual system which its individual parts do not correspond immediately to experiential facts, but it is a part of a theoretical construction that is true or false. This is corresponding or not corresponding to experience only as a whole. Already some scholars attracted our attention to this passage, most of all Don Howard, who is insisting on the importance of the possible influence on Duhem in this passage. I don't want to enter into this question. The only point why I mentioned this passage is I think here we find the conceptual tools that Einstein had at his disposal when he will be discussing about the role of rods and clocks in his theories. So the opposition is not that between principal and constructive theories, but the oppositions between an epistemological model in which there are individual parts of the theory which are coordinated by the behavior of some existing physical system, and an alternative model, somehow more vague, in which this correspondence does not happen, but still we have the way to connect the whole theory as a system of interconnected theoretical concept with a whole body of interconnected physical facts. The only point that was important is this is the problem Einstein had in mind when he will be discussing the role of rods and clocks in his theories. Let's start with a real question now, the problem of rods and clocks in both relativity theories. So we know that special relativity rods and clocks can be used to measure directly coordinates, which are measurable quantities. In general relativity, coordinates difference are not measurable quantities anymore, but still a line element ds is measurable using rods and clocks. Identical rods and clocks will always measure the same line element ds. This is probably Bessel might have remarked to Einstein in private conversation or in a letter we have lost, that got lost, that here there was a problem. There was a presupposition Einstein was not making clear. The proposition is, I quote again, your comments about equivalence of physically different measuring rods and clocks and subjected to different prehistories, we'll find this word again later, is fully correct. However, this assumption also tacitly plays a role in the Galilei-Newton's theory. There's an obvious assumption. I'm not discussing it. We will see it will be not so obvious. But this is the central question he is discussing. So we need rods and clocks that, again, when they brought back together, when they're close together at relative rest, whatever would happen to them in the past, whatever the intermediate histories might have been, they always measure the same proper time, the same proper distance. There is a fundamental presupposition of the theory that Einstein at that time thought it was simply obvious. Well, let's see what we meant by rods and clocks. Let's see what a physicist at the time would think of a rod, of a clock. And I here simply follow an example, simply the quote got lost, but by Ludwig Flamm, was an Austrian physicist who wrote a paper in 1916. And he makes very, very intuitive example or to show what we can use as rods or clocks in GR, or what a physicist at the time would use. So we can use a rock salt crystal as a rod, and a cadmium atom emitting its red line as a clock. So literally we take n spacings between the atoms of the crystal as a unit of length, putting n wave crests emitted by the radiating atom as a unit of time. Which atom with which number is not important. The only thing that is important is that the ratio of units is an absolute constant. This means simply that we defined in this way the equality of two, for instance, to spaceline ds in terms of the same number of lattice of a crystal. The choice is arbitrary. The equality of two time like that ds as the same number of wave crests of our cadmium atom. What's the problem with this definition? We have to assume, we are talking about general relativity here, of course, now. Rods and clocks are not affected by the gravitational field, or the dynamics governing their material structure does not depend on higher derivatives or the second derivatives of the German, put it more elegantly. This might be, Einstein could consider that as a consequence of some version of the equivalence principle. But second, we have also to assume that, for instance, Rosen clocks are not influenced by other external influence, for instance, the electromagnetic field. But it's, of course, not at all obvious. So we consider rock salt crystal has regular arrays of positive sodium ions and negative chlorine ions, which maintain this position with electric forces. So we put a charge in a crystal, we expect the crystal to be deformed. So cadmium atoms, again, of course, electrons running around the nucleus. We put it at an electric field, we will observe the Stark effect, and so our clock will not be reliable anymore. So this is only to make clear that Rosen clocks are very complicated systems, so they are necessary, indispensable to give content to a theory, but their behavior cannot be decided without having a detailed knowledge of the physical structure. Why is that so important? Let's make a very simple example. Gravitational redshift already mentioned. So let's take a clock at rest in a gravitational field, the sun's gravitational field. So the relationship between the proper time and the coordinate time is given by the simple formula. So two atoms of the same systems are two identical clocks. So if measured with a spectroscope at rest, they will show the same spectral line. So take two identical atoms, one on the sun, one on the Earth. We assume that we measure the same proper time, but since the geometry is non-Euclidean, there is no coordinate system, so will they measure the same coordinate time. So the factor G44, or the square of G44, is responsible for the fact that the spectral lines of the solar atoms will be displaced respect the spectral lines of the Earth atom if they're both measured by a spectroscope at rest on the Earth. Of course, this is, if we observe this effect, then the theory is empirically confirmed. The problem was at the time that no one could observe this effect. So where people were starting to suggest to Einstein that he could drop the other assumption that the atoms are perfectly identical on the sun and on the Earth. So the empirical content of the theory, on the one hand, depend on the assumptions that we make about the behavior of complicated physical systems just like atoms. On the other hand, this behavior is controlled by physical laws that have nothing to do with general relativity, about which we don't know so much, by the way, at the time. And so the empirical content of the theory is somehow in a shaky position. It is actually what Einstein had in mind, probably, roughly, and put it, of course, in a more intuitive way, when he wrote a long letter to his former student Walter Dellenbach at the beginning of 1917. It's a very important letter for my talk, I mean, in the sense that here Einstein defines his position towards the issue of rods and clocks and relativity theory in a way that will never change throughout his life. We will see would change the nuance and the use that they make of this approach, but not the fundamental point. So let's analyze this passage more in detail. So, dear Dellenbach, your remarks are, in my opinion, largest and correct. They are speaking about the private conversation. Strictly speaking, the d square cannot be rigorously considered as a result of measurements, not even in the absence of the electromagnetic fields. We don't even know if the gravitational field, he says in a footnote, might modify our rods and clocks. Nevertheless, in a didactically reasonable presentation of the theory, the d square must be so considered as if were rigorously measurable. The issue here is analogous to that in electrical science, where the definition of the electric field strength and magnetic field strength are given, even though these definitions do not withstand strict criticism. It's a very important comparison that will return again and again. He said, further, a logically satisfying presentation can be achieved so that a single, more complex solution is related to the observed facts. Then, in this case, a measuring rod would be an atomic system of a certain type that does not play any special role in the theory. When will we reach this conclusion? We will reach this conclusion when we will have a theory of matter within relativity theory. There's something in between. But at the end, Einstein seems to show more preference for a continuum theory of matter. So we are better placed with a continuum conceptions, that is, a theory of field theoretical theory of matter developed within the framework of general relativity, because here the building blocks, the electrons, will appear not provided from the outset, but will appear as solutions, fundamental solutions of the theory. Then, given the electron, I can, and the interaction between the electron, I can explain the existence of stable bulky material structures. Some of them can be used, for instance, as rods or as clocks. This will be the proper way to put the theory. Simply, the theory that I have is not enough powerful to reduce a full theory of matter, so I stick with a less precise way of thinking, where I assume that there are rods and clocks in reality that behave in a certain way. The theory makes predictions about their behavior, and I observe the behavior, and then I claim their theory is correct. But this is only a provisional point of view. So all the elements that we find again are all in this letter. The difference between a provisional and a principal point of view, the question if rods and clocks are independent entities or if they should appear as solutions, and at least an allusion to the fact that, of course, the comparison between the theory and the experience will change a lot when we will have the final theory, in which rods and clocks will appear as solutions of the fundamental equations of the theory. Dellenbach was Einstein's former student, but he was also, at the time, Hermann Weyl's doctoral student. So at the time, exactly some months later, Weil will give his famous lectures on relativity theory. It will become Raumzeitmaterie in 1918. And in this book, he makes a very similar remark. So it's clear that probably Dellenbach discussed this topic with Weil. Definitely, speaking here of special relativity, actually, definite exact statements about the behavior of origin rods and clocks, and he's referring to the fact that identical clocks, identical rods always measure the same proper time, the same proper distance, can be made only when we have built a dynamics based on physical and mechanical laws. When we will have a proper theory of matter, special relativistic theory of matter in this case, then rods and clocks will be treated as physical systems just like any other. Only in this case will we make a proper use of them. So actually, Weil tries not to use them as far as possible. Just thereafter, Weil sent the drafts of the book to Einstein in March 1918, and a paper, which I think this letter, but and the draft of a paper on an idea of unifying electricity of electromagnetism. Of course, this is a very well-known episode. Many of you will know very well, but I have to at least sketch it very briefly. One can consult the literature for more details. So, very roughly, one can put it this way: the quality of 2ds is path independent. Let's assume that the quality of 2ds is path dependent. Then we will get some new quantities that I can interpret as the electromagnetic fault potential, and I will get a theory unifying gravitation or electromagnetic field, at least geometrizing the electromagnetic field. Einstein immediately expressed worries. So my theory is based on the fact the same number of ticks or two identical clocks defines the quality of 2ds. If I drop this assumption, then the relativity theory will fully lose its empirical basis. Fortunately, and this is roughly his reaction, nature behaves differently. Since sodium atoms and electrons of all sizes do not exist, so atoms are all identical, and I use atom as clock, then the time like ds, the quality of time like ds is an absolutely defined, or the ds is an invariant. Of course, here Weil forced Einstein to assume a quite strange position, because in which the behavior of some non-classical systems justify the assumptions that a ds is a physically significant invariant. But the reaction of Weil is simply saying, as we can imagine, okay, how a clock really behaves, that should be decided by computation of the dynamic space on physical laws. You cannot simply say there are in natural systems that works like that. You should have a theory that from which this behavior of rods and clocks actually comes out. So the opposition return to another exchange electron with Dellenbach is simply the following. So Weil and Dellenbach were objecting to Einstein, you're using too complicated stuff, rods and clocks. It seems to me arbitrary to give physical content to your theory. And Einstein recognized the point. Actually, Weil is right. They should appear as solutions. He had admitted that in the previous letter. However, Weil theory is not as powerful as he thinks. He cannot do that. My theory is not. So for this time, I'm very comfortable by the fact that an enormous amount of spectroscopic evidence shows me that all atoms are identical. Einstein was at the time not rejecting Weil's theory immediately. There was a lot of other letters, of course, but he was started to be very much interested in actually developing a theory of matter within general relativity. This is the first paper in working on that, which says the possibility of construction of matter out of gravitational fields. Also, the Einstein-Kaluza correspondence shows clearly that a good theory, it says to Kaluza, we propose a theory with the fifth dimension, should explain the existence of elementary quanta. Without that, in my theory, a good unified field theory would not. So unified field theory would not be good. So this was the project it was starting to develop. It will develop in the following years. But another figure emerged on the scene, which is there's another well-known episode that I have to mention to make sense of the subsequent part of the talk. It is the young Wolfgang Pauli. He was 19. He already wrote a paper on GR, and he was working on a paper on Weil's theory. They sent to Weil. And in this paper, in one of these papers, there are two papers actually. In one of these papers, there is this what he called a physical conceptual objection, which is quite famous. Pauli introduced what he calls an observability criterion. This is the constant electric field strength in the interior of the electron is a meaningless fiction. So he's saying all these theories, Weil theory in this case, they try to treat the electron as a knot in the field, as a part of the field which is very concentrated. Then they have to define the field strength inside of the electron. But of course, there are no smaller. But how do you find the field strength? You define the field strength using a test particle, but there are no smaller test particle than the electron. So you cannot put a test particle inside of the electron, in principle. So it doesn't make sense to define these quantities in this case. Weil's reply was somehow evasive. It says, "Yeah, no, actually, I don't need that. I can infer the field strength inside of the electron from the behavior of the electron, or an external behavior of the electron." But Weil simply never bought into some sort of operational way of thinking. So his reaction is understandable. But Einstein's reaction is more interesting. But he clearly felt that this objection was a serious objection, not only against Weil's theory, but against everyone's continuum theory, and this means against my own theory that I'm trying to develop. But Einstein says to Born, without entering into detail, still I will pursue this project. I think the continuum theory is a good theory. So it's clear that Einstein must have in mind some other epistemological model that he could think would be reliable in the case in pursuing his new project. So these are all private correspondence, but it is clear at a certain point the discussions became public. There are other letters one can mention, of course, with other people, but the next important event is the Baden-Powell meeting in 1920. There's a famous meeting for other reasons, but also for the discussions after several papers, one of them of Weil, about his own theory, and Einstein replies with the usual objection. If I consider two appliances measuring rods and clocks, according to the experience, their quality is independent of their prehistory. So now this assumption must be made very clear, and now you see every presentation of Einstein's theory will have this assumption explicit. We mentioned this assumption explicitly. The possibility to attribute to two neighboring points a number ds, which possess a physical meaning, is based on this assumption. Without that, the ds has no physical meaning. But Pauli replies as to Einstein, but then, look, you cannot define the electrical field strength inside of the electron, So the similar statement should be made about measurement of space and time, because arbitrary small rods do not exist. So remember that Einstein tried to develop his own theory of matter, in which electromagnetic field and gravitational field will both play a role in assuring the stability of the elementary particle. So if you want to develop this theory, clearly your epistemological model will not work. So if you say that the geometry around the sun is non-Euclidean, then you can make this sentence as an empirical meaning, because you can really observe the behavior of atoms. But if you say that the geometry inside of elementary particle is non-Euclidean, what Einstein claims in a paper of the time, for instance, then this statement does not have any physical meaning according to your own criterion. So Einstein's reaction is pretty interesting. It's very seldom mentioned, but I think it is evasive. But looking at what we'll say just some months later might be very interesting. With increasing refinement of system of scientific concepts, the manner of procedure of associating the concepts with experiences becomes increasingly more complicated. So if a certain scientific study, one finds that a definite experience cannot be associated any longer with a concept, then one has two choices. One drops the concept, it was what Pauli wanted to do, or keep the concept. How can you do that? I have then to change my epistemological model. In the latter case, one is forced to replace the system of associating concepts with experience by a more complicated one. In the case of comes to spatial and temporal distances, also we have this alternative. So which is this alternative? Which is this more complicated epistemological system? I think that the answer can come from the reply of Einstein to a talk of Max von Laue, where Einstein says that after saying to Weil that it was absolutely fundamental to measure the ds with rods and clocks, he here say actually it is a logical shortcoming of the theory of relativity in today's form that measuring rods and clocks must be introduced separately. They're independent entities, they're simply there in nature, instead of being constructed as solution of differential equations. This would be the final theory. Of course, in this case, that we will see briefly, the epistemological model in which I compare the theory with reality will become very different. So which is the epistemological model we are talking about? I think a good way to put it is a talk that Einstein gave to a radio station. We have the audio recording. And he says this sentence at the beginning of January 1921, the invariant ds is connected with the several effects measured using rods and clocks, just like it happened to the fundamental concepts of Maxwell theories through Heinrich Hertz. This is the epistemological model he roughly used in his works. The ds is an empirical meaning because I measure it with rods and clocks. So it's this epistemological model that they have to now put into I have to find an alternative to this epistemological model. So now just a few days later, Einstein gave his famous talk, Geometry and Erfahrung. There are a lot of research on that. So Michael Frieden wrote, of course, the fundamental paper on this lecture. I would like to try here, without entering any details, simply to try to show how much in this, not everything, but a lot of stuff in this lecture is somehow an attempt to reply more clearly to what happened at Baden-Nauheim. So Einstein says, "Su specia temporis," so that's not, he doesn't say that, but de facto is that. So in the present stage of development of theoretical physics, so rods and clocks must be employed as independent concepts. That's what independent concepts. What is the problem with this epistemological model? It says that explicitly. It breaks down when applied to spaces of submolecular order of magnitude. It was Pauli's objection. So this model failed exactly in this case. What I can do, again, a little bit of rational reconstruction, but then I can pass to another model. Sub specie aeterni, rods and clocks actually are not indispensable, are not independent physical systems, but they should appear as solutions of my fundamental theories, as simply physical system, atomic system, just like any other, and will be appear of solutions of my theory. So at the end, only geometry and experience, geometry plus physics, will be compared to experience. As a famous statement of Einstein's that he attributed to Poincaré. But I think that the reference to Poincaré should be understood more as a, let's say, a rhetorical way of alluding to a problem that was emerging in his work on a unified field theory. So the goal he wanted to reach is the following. In a pure field theory, the field variable produced by the field in an empty space, as well as electrical elementary particles in contiguous matter, will be both described by the same theory. Of course, in this case, rods and clocks will appear as solutions, just like any other physical systems, and then clearly only the psychoepistemological model would be legitimate. This is what Einstein repeats again and again in a lot of other writings, talks along the years in the 20s. One is they're all more or less famous. This is particularly famous. This is Nobel Prize lecture. Again, it is unjustifiable to start with an artificially isolated part, rods and clocks. Logically, should be more correct to begin with the whole of the laws, including those explaining elementary structures matter, of which rods and clocks are made. So usually it says more explicitly, I start with rods and clocks. The required or general covariance is verified by the fact that it makes predictions by the behavior of the physical systems. Then I apply this requirement also to the laws describing the macrostructure of matter, so that is to the laws that are responsible for the very existence of my rods and clocks. It should be better to start with these laws from the beginning and not from the rods and clocks as unstructured entities. He put it in a more philosophical way in his review of Kant and Einstein. So Don Howard, for instance, mentions this passage a lot of times. Two standpoints: one grants right to a particular rigid rod, geometry is empirically testable, or only geometry and physics are testable. In another paper just some year later, standpoint I, just like Helmholtz, and without that, relativity theory would have been impossible. Standpoint B resembled that of Poincaré, and this is what I need, and it will be the system that I will use in when physics will be in a later development. In this, the entry space-time for the Encyclopedia Britannica in 1926, it said something even a little bit more articulated. The ideal of a rigid body is an abstraction that is well rooted in the laws of nature. I can use it. Geometry comes from that, and it is explained in as the science studying rigid bodies. But of course, rigid bodies are not compatible and commensurate with elementary particles, with structural constituents of matter. But of course, consistent thinkers, as I mentioned here, told me that actually what I compare with experience are geometry and physics conjointly. I think many other passages can be quoted from stuff from the 30s, but I think it is worth to come back again to the real important oppositions. He repeats again and again. This is a not well-known letter to a British physicist called Swan. I've forgotten his name. A British-American physicist, actually. And he says, it's a long, beautiful letter, but the key of the point is the oppositions between this point of view. So measuring rods and clocks are treated as independent physical objects. I got lucky. In nature, there are physical objects that behave just like I need to behave, and I can use them to give physical meaning, in this case, to the coordinates. He's speaking about special relativity. In principle, however, rods and clocks should be treated as solutions under the basis of structural laws, means fundamental physical laws. Some modifications of nonlinear modification of Maxwell equations, I will have the electron as solution. From that, I can reconstruct more complicated structure of matter, including my rods and clocks. So everything we have then said so far simply somehow, put it wiggishly, converges to what Einstein's wrote in 1946 and published in 1949 his autobiographical note. This is the key passage that everyone quotes in this debate, especially Harvey Brown. Harvey Brown mainly refers to this passage. But this passage doesn't say anything new, actually. As this very same passage, I won't read everything, only the parts that are highlighted. So there are two kinds of things. One is struck by the fact there are two kinds of things in my theory. Measuring rods and clocks and all other things actually would be better if rods and clocks appear as solutions, just like any other physical system. My theory, unfortunately, was, and it is not strong enough to deduce their existence. Anyway, I should not legalize the mentioned sin. I hope that I will find a better theory in which I will find that rods and clocks are solutions to the fundamental equation. So I should not stick with the idea that intervals are physical entities of a special type, intrinsically different from other physical variables. And he makes the remark that probably new, reducing physics to geometry. So he probably refers to an issue that Dennis Lenkel has written about. Starting from 1926, Einstein repeated to several correspondents that he didn't want to geometrize physics. And here, that's my interpretation, seems to say that actually we talk about geometry in spatial or in general relativity only because we make measurements of this fundamental variable with what might call geometrical measuring instruments, measuring rods and clocks. Of course, in the final theory, these measuring instruments will be treated just like a physical system, just like any other. So the very idea that I'm talking about something specific called geometry will fade away. The point will be that I will unify the gravitational field and the electromagnetic field. It is important, this reference to unified field theories, because I think when we pass to the second part of the book, the sort of reply to criticisms, where Einstein's reply to all the people that wrote several papers in this Schilp volume, where the autobiographical notes were contained. Here, one understands more why Einstein insisting again and again on the fact that rods and clocks at the end will show the appearance of solutions. First of all, the point is, can a spectral line be considered as a measure at a proper time? Is the natural measuring stick independently of its position in four-dimensional space? This was the explanandum. So there is a point where I disagree with Brown. So not the contraction of rods and clocks, but explanandum is the very existence of good clocks and good rods that always measure proper time and proper distance. However, the assumption of the existence of physical objects in the macroscopic field, is talking about general relativity now, and measure the invariance ds, it's plausible but not necessary. In a complete theory, as the physics of a totality is referring to possible unified field theory, then the objects used as a tool of measurements, rods and clocks, will not live in independent existence alongside of the objects implicated by the field equations. So the very idea that the independence of the physical system will be eliminated, and it will appear a solution of the theory as any other physical system. Why is emphasizing that? I think that emerged quite clearly. The points might be the following, just a few lines later. So it says, if one disregards quantum structure, one can justify the introduction of G mu nu operationally. What does it mean? Then I have this epistemological model. General relativity equations make some predictions of the value of the G mu nu. The G mu nu are actually measured by rods and clocks. These predictions correspond to the behavior of the observed behavior of rods and clocks, and the theory makes correct predictions. But of course, when I apply my theory in a future unified field theory to the microscopic, then this model simply collapses. Then I have to use a different epistemological model, where Einstein's introduced at a certain point, and he insists a lot, for instance, in the lecture in Oxford, which John mentioned in his talk. The field equations now should be considered correct, not because they correspond to observed behavior of rods and clocks, but because they're the simple, generally covariant differential equations which a metric G mu nu can satisfy. Sorry, it was a mistake. Can satisfy. So this is the new criterion I will use. I think that is really what is the key point of all the discussion about rods and clocks. This emerged from a letter about the same time to his friend Michele Besso. Dear Michele, in a consistent field theory, there is no real definition of the field. In this way, we arrive really to a Don Quixotesque situation in which there is absolutely no guarantee if it is possible to know if the theory is true. A comparison with empirically known can only be expected to come from finding exact solutions of the system in which empirically known structure and their interactions are reflected. So when I find solution corresponding to electrons, positive and negative electrons, the particle that he knew, even at the time he should know better, should have known better, then I will somehow could claim that my theory says something about reality. So physicists had good reason to reject my ways unfruitful. However, slowly we realize that they will realize that a quasi-empirical method, with the quasi-empirical method, one does not approach the things in deep. So to really understand my point of view, you must read my answer in the shaped volume. So he was exactly talking about this problem. His new theory simply does not have, it is hard to say what does it mean that the theory is true. So the problem is, and he says this exactly a little bit later in the volume, I have to answer Pilot's famous question, what is truth? And here clearly he introduced, after a longer passage I will not mention, there's a debate between Reichenbach and strange debate between Reichenbach and Poincaré. But at the end of this debate, it says, he simply refers to his somehow naive epistemological model, individual concepts which occur in a theory does not require any specific justification. They are only indispensable within the frame of the logical structure of the theory, which in its entirety validates itself. That sounds a lot like what he said in 1911, just without making any connections between stuff written 20 decades later, but it's the very same oppositions. Individual parts of a theory versus the theory as a whole. So let's go to the conclusion. The key elements are very simple. So there are two different, the opposition between two different problems, as Browns rightly saw, between rods and clocks as independent objects and rods and clocks as solutions. But the point is, it's nothing to do with the contraction of rods and clocks and the slowing down of contraction of rods or slowing down of clocks. It's nothing to do with the natural space-time. The question is a simple epistemological question, is the question of the relations between the theory and experience. So Einstein somehow knew that testing a theory is complicated stuff. I can start with some early definitions that I can use at the beginning, drop then, so this definition might be rejected at a later stage of the theory. So he said that explicitly, talking about the notion of rigid rod to his friend Maurice Sullivan, unless one sins against logic, one generally gets nowhere, or one cannot construct a bridge without using a scaffold, which is really not one of its basic parts. So the notion of rods and clocks were not basic part of the theory. It will be discarded at when I will find the final unified field theory with a theory of unified field theory with a theory of matter. If you have time, I will simply make a last step to convince you that it is roughly the problem we are talking about here, because this problem emerged in exactly the same way just thereafter, in the 60s, when general relativity became again a cool theory to work on. So the great relativists of the time discussed about the very same issue. So we have a guy like Singh was a classical operationalist. I methodized my clock with atomic clocks. Why I do that? Spectroscopy is a remarkable. Show me that there's a remarkable order in what we call atomic clocks. That's enough. So, but people like Wheeler, Robert Marxer was his student. They clearly found this unacceptable. Why I should refer to another theory to give my theory empirical content. This is not acceptable from an epistemological point of view. And the model most relativists accepted from the time is simply this model emphasized, we find in James Anderson famous handbook, a fundamental requirement of the theory is to be complete. By this we mean that it must contain a description of all physical systems which is purposed to deal, including those systems employed in the measuring properties. The theory must discuss physical systems and the clock that used to measure time within the same framework. Thank you. Want to see the old paper is this one.